So I guess we can get started. And hello, everyone. Olá, pessoal. My name is Aldebaro Klautau, and I'm a professor at Federal University of Pará. It's an honor to be hosting this plenary session of the Brazilian Symposium in Telecommunications and Signal Processing. We have here Professor Tim O'Shea. He's the co-founder and CTO of Depl, a venture-backed startup building machine learning-driven wireless capabilities and optimizing 5G radio access network and OpenRAN deployments. He also serves as a research assistant professor at Virginia Tech in the United States. He has extensive contributions to machine learning for communications, and many of us are aware about his seminal work in end-to-end learning for the physical layer, modulation classification using deep neural networks, and other topics. And among other things, he helped build and lead the GNU Radio projects. He's currently the co-chair of the IEEE Emerging Technology Area on Machine Learning for Communications and an editor for Transactions on Wireless Communications and TCCN. In the name of our society, I'd like to say thanks again to Tim for accepting the invitation and emphasize that it's a big pleasure to have him. Please, Tim, feel free to start.
Awesome. Thank you for the intro and for inviting me to speak with SBrT. I wish I could have come to Brazil, but maybe next year. So I'm going to talk a little bit about leveraging machine learning on the edge within OpenRAN, vRAN, within 5G, and also beyond 5G in the RAN. And some of the work we've been doing, and I think some of the trends that I think are really exciting in this area right now that will be transformative in the industry. So looking at where things are today in wireless, we're seeing more and more device density. So device count, we've gone from 20 to 30 billion devices today to looking at 75 billion devices in 2025, and then predictions of 15 devices per person at least by 2030. So we have these massive needs for more bandwidth, more coverage, more density, more spectral efficiency, and more spectrum. And I think that I look to machine learning as a way to enable this. And so some of the needs, the demands in this entire field right now are having more efficient multi-user spectrum utilization, better power efficiency, better QoS for the range of different application requirements that are out there, and better utilization of difficult new bands like millimeter and terahertz wave. And so there's the 3GPP class of protocols, but we're also inundated with new protocols like Sigfox and LoRa and NB-Fi and NB-IoT. So there's many wireless technologies trying to fill this need over the next decade. So the fundamental reason I think that machine learning is useful in this wireless space is that we have these really nice exact solutions from physics. We have Maxwell's equations and Snell's law, and we have tools like ray tracing for EM propagation modeling. But when we start looking at these really complex deployment scenarios, like many different materials in an indoor environment, many different emitters in the indoor environment, and then these very complicated outdoor, urban environments, even modeling these in a statistical parametric way is extremely complex. So we don't know all of these properties, the geometries and the surface properties, the near field effects of all of the devices and objects in this area. And so doing this really precise modeling in this traditional physics and statistical modeling approach is kind of intractable as we want to exploit more and more of the channel in these propagation environments. And so with machine learning, we turn to data to try to model this, and often sounding data and channel state information So either way you approach it, if you want to model the complexity of these propagation environments, you can't escape data. And so right, and so really I see that machine learning and exploiting this measurement data is the only way to really scale to the complexity of the modern wireless channel environment. So, I think from my own investigations, I think we've split this into basically two pursuits, which I think are the two halves of the same problem. One is simply understanding all of the emissions in the spectrum. So who are the other users that you're sharing the spectrum with? What are the interferers or the distortion effects or the different emissions in the spatial spectrum that we need to be aware of and to work around? And then when we access the spectrum in our radio access networks, how can we really maximize this multi-user efficiency and the power efficiency, and then ultimately the user experience? And so these are really kind of the two major problems that we need to continue addressing to get better and better spectral utilization and performance out of these networks. So the way we've done physical layer design for many, many years is to split it up into this nice chain of well-defined problems where we do source coding, we do channel coding, we do modulation and pulse shaping, and then we have some access scheme. And we have these really nice simplified statistical models of each one. So we might assume Poisson arrival process in the multiple access scheme. We might assume, a Rayleigh or a TDL fading model within the estimation and equalization. And we may assume a binary symmetric channel when we're working on the channel encoding and decoding. And then when we're doing estimation, we may consider performance of these estimators under a Gaussian or a simple Rayleigh fading channel. And so this has gotten us very far, and it's gotten us excellently performing systems, but I think we're getting closer to the point where the barrier is now the quality of these channel model assumptions. And so what we've tried to do is look at this as a machine learning problem. So rather than modeling each of these individually, can we learn a non-parametric neural network encoder and decoder model that is able to compensate for a wide variety of different channel effects and conditions based on measurement rather than these statistical channel model assumptions. And this is exciting because we can, in a way, simplify this, but then we can also look at more realistic channel measurements and channel conditions for our systems in their deployment where we really want to optimize them in the real world systems. So, we've done some work in the kind of abstract, so outside of the standards, to look at, can we build end-to-end autoencoder-based communication systems that simply learn how to transmit and to receive that data kind of naively without being specified a specific modulation or coding scheme. And it's really exciting to see these systems converge and come up with a good solution on their own. And then especially when you start putting impairments into these systems. So on the bottom right here, we're showing this is a software radio-based system and kind of a point-to-point communications link, but where there's amplifier distortion going on at these higher amplitude points. And so here you see the 16 QAM starts to get quite a few symbol and bit error rates. And so as a result, your frame error rate here has dropped to roughly 30%. Whereas if you allow an adaptive autoencoder-based system to learn a new modulation and then learn how to decode that over this same impaired link, you come up with this kind of very unique constellation, and it spaces the points out more evenly with regard to the different noise variants at different amplitudes. And ultimately, we're able to get here, 75% frame error rate. So this is just kind of an example of how, when we rely on a learning-driven system that's not constrained by our traditional modulations and encoding schemes, we can sometimes do a lot better. And this is still kind of the point-to-point case. So it's just, single user and a single kind of hardware impairment. But these benefits really can compound when you start adding multi-user, multi-antenna, and all of these different constraints that you'd like to optimize over jointly. Right. So then there's this question of, well, what constitutes end-to-end, right? So in this previous example, it was simply code words or frames. But there's a lot of ways to think about casting a communication system as a machine learning problem. So, we've looked at, can you do this over MIMO configurations where you're learning new nonlinear multi-antenna encoding and decoding techniques? There's been some really cool work looking at what happens if end-to-end is actually on content. So it's on something like an image or text or speech that has a lot of structure to it rather than just whitened bits. And some of the results there are very, very promising, where, for instance, in this work, learning a joint channel source code for imagery that goes directly from an image distribution to the symbol distribution over the air, you're able to get on the order of 10 or more dB in some cases. So this could have major capacity implications for certain types of content broadcast. And then, of course, multi-user schemes. There's a lot of really interesting ways to share both spectrum and spatial degrees of freedom. Today we do this primarily with OFDM and multi-user MIMO, but I think that there's a number of different schemes that are maybe less heavily constrained that we could consider in the future. And then all of these other aspects of quantization, channel state feedback, frame and pilot design, and especially optical systems where they're heavily distortion limited, could significantly benefit from this sort of end-to-end learning. So I think it's really exciting to see all of the ways in which this approach to the comm system design problem could start to transform, how we build comm systems. So at the same time, so if we look at, taking a step back into systems that are being built and deployed today, we've seen this massive acceleration of OpenRAN and this kind of open virtual RAN ecosystem over the past year. And the idea here is that, traditionally we have this proprietary BBU that's implementing your L1, 2, and 3, typically with kind of a closed front haul to a radio head. And this transition to having open radio units along with open distributed and central units, along with these kind of open services that can help optimize and tune these across the network, are really exciting because we're starting to open up a lot of these RAN components for more innovation and for trying out many of these new methods in more flexible ways that can really help with performance. So if you look at the ORAN architecture, from the edge side, you've got these open radio units pushing OFDM grid data back to the distributed unit, which is doing the L1 and some of the L2 and L3 processing. And then you have the central unit finally back to the core. And so I think from a R&D perspective, it's really exciting to be able to start using commercial grade equipment and software, and being able to plug in and validate some of these algorithms within production hardware and production software environments. So OpenRAN, I think, to me, is very exciting because it's making the commercial PHY accessible for folks doing algorithm research, and allowing for a lot more innovation. And it's also very much needed. So the tier 1 vendors have put a lot of work into heavy optimization of their RAN. And so OpenRAN needs this innovation and this performance optimization if they're going to compete and be a really viable, high-performing alternative in the future. And I think this is exciting because we have kind of a green field in machine learning communications research, and then now we have a business green field in how can we insert these capabilities into OpenRAN networks where they can really help improve performance and experience and cost for these deployments. So our focus has been really heavily within the distributed unit, within the 5G layer 1 PHY. But I think there's also been really heavy research by a number of folks in the L2 and L3 looking at scheduler and resource optimization, as well as application-specific ML applications that can have very low latency access to 5G devices over the radio link. So some of the things that we've kind of learned looking at this are that if we focus on machine learning within the L1, really the goal here is to learn better performance from the local channel. So rather than starting with the statistical channel definition, let's try to cope with the impairments and the effects we see in a deployed cell. And then let's learn to suppress any local interference or bad effects that are present, that we may not have models for or we didn't know about at the design time of these L1 algorithms. And so one of the things we're showing here is basically a simple software radio-based TDD 5G system where we're operating in an ISM band, and there's a lot of interferers bursting throughout the band. And so this was kind of exciting to see results because you can compare their traditional MMSE approach with a fully end-to-end learned approach. And you can see that in these cases, you can learn significantly better how to cope with interference events. So if there's bursty interference in the band, we're often seeing 4 or 5 dB better EVM during those events after kind of learning in that environment. The other really exciting thing here is that standards don't necessarily need to change to be able to leverage these techniques within 5G deployments. So a lot of these sorts of end-to-end learning approaches can really be implemented transparently. So if we look at the functionality in the current GNOB stack, we can just think about implementing these in machine learning rather than having to change any of the protocols or fields that are transferred. And I think there's even more possibilities in the long term as the 3GPP standard evolves and starts opening up more protocol and feedback fields that can extend what we can do just transparently today. But the other takeaway was really that measurement data is really critical. So simulation, doesn't capture the performance benefits that we see over the air, often because we can't simulate all of the effects. And then when we do simulate effects, they're often, whitened distributions. Whereas, when you look at the real world data measurements, there's more structure and more ability for learning and coping with those effects. So for some areas, I think in future phi research, these statistical models really won't be sufficient to be able to capture and to demonstrate, how well these algorithms work in the real world. Some other interesting things to look at are if you're looking at machine learning on the layer 1, well, how can you scale this to multi-user systems? And so this was a 4-user TDD system over the air, and looking at well, how well can you learn L1 estimation and equalization across all of those users jointly. And here we saw that you could converge to a solution for all the users still, rather than trying to train for each individual user, and that this worked faster, and you could still outperform the kind of statistical model. And so there's a lot of need to really scale these sorts of experiments up. Once we have a macro cell with hundreds of UEs, showing that learning still exploits more structure in the channel and propagation environments than the kind of naive statistical model, is really an important point to show the benefit of these sorts of approaches. But in these cases, we were seeing, 5 or 6 dB BER and EVM improvements over the MMSE approach, and especially during these interference events again. And then finally, to really validate and deploy these within 5G, there's these standard sets of TDL channel models that need to be demonstrated. And this is some examples of the TDL tests within NR. And we're starting to show here that in this case, you can look at some of these 1x4 and 1x8 MIMO configurations that are standardized, and look at some of the standard TDL channel models. And even at very low SNR, so on the left, we're looking at 16 QAM at 6 dB SNR in a 1x4 environment. And on the right, we're looking at 1x8 QPSK in a minus 8.7 dB environment. And then both of these cases, if you start to learn how to do the estimation and equalization and combining, rather than following the traditional MMSE and Wiener filtering approach, there's a significant gain in both of these. Even though they're kind of built from a whitened TDL distribution, you can get up to 50% bit error rate reduction, or 30% in this case. And so this is really exciting from the perspective of helping extend coverage and just get better spectral efficiency within the sectors and within the existing infrastructure and hardware within 5G deployments. So kind of switching modes to the sensing side, I think we've seen dynamic spectrum become much more realistic over the past couple of years as well. So I know we have CBRS taking off in the US to launch next year, and we have the 6 gigahertz band now opening up for unlicensed use. And so we're seeing many of these bands become much more dynamic. And so the initial approaches are very much database driven. So in CBRS, primary and secondary and general access users all need to register with and query a database for authorization. But we've seen that the kind of statistical propagation models that try to pack all of these users into the spectrum, are not that accurate. They're still very simple models. And so there's a massive need for better machine learning propagation models to help pack devices closer together and have higher aggregate spectral efficiency. And I don't think we can really get there without sensing and without this feedback system from all of the different nodes in the system. And then if you look at the 6 gigahertz band, we're looking at this kind of very heterogeneous set of protocols. We're going to have LTE unlicensed, NR unlicensed, than Wi-Fi 6E, along with probably other technologies. And so there's really this increasing need within these private networks to be able to understand what's out there, what is using the band, and what are the adjacent sectors and carriers that we need to avoid or optimize for. And so I think we're really driving, we're seeing more and more need for this kind of spectral awareness within the RAN. So if we then think about how do we build these sorts of sensing capabilities, there's a number of techniques we've used for many, many years, looking from the most general that are just kind of energy detection based, which I believe are what some of the ESC capabilities in CBRS are bound to use, all the way up through very protocol specific techniques like matched filtering or cyclostationary feature detection for specific features. There's kind of this trade space between design and computational complexity and then accuracy. And what we really need for this to be viable and effective on a wide scale is that these models are very accurate, they're very low design complexity, and they're very low computational complexity, so that they can run on low-cost devices, and they're not burdensome within these networks. And then we can see, if you look back to kind of computer vision as an analog, these same two axes of accuracy versus computational complexity, that we've seen this migration of, as we get better and better at building and training neural networks, we move kind of up and to the left. So we're able to keep making these networks smaller and faster and cheaper, but also make them more and more accurate. And so this trend is continuing. And as we apply these sorts of machine learning models for sensing, they just keep getting smaller and faster and more accurate. And so we have this curve in which, we're just continuing to get better and better than these kind of baseline approaches. And so it's just kind of the natural way to do effective spectrum monitoring. So these are just a couple examples of that. Some of the earlier work we did using convolutional networks to do modulation recognition, demonstrated that you can get significant sensitivity gains on the order here of about 6 dB for single carrier modulation recognition when you're trying to identify an emitter in some environment, as well as lower complexity. So I think in this case, it was on the order of 3 times less multiply accumulates to do the same operation. But it also pointed out that this RF domain knowledge is important. So you can't just take computer vision models and apply them directly here. The data needs to really match the target distributions in the world. So we need very good simulation and propagation modeling to augment and train these systems robustly for all of the sorts of wireless effects that they're going to see in the world. And then more recently, some work from Nathan West looked at the problem of just wideband detection rather than just signal classification. And so this is if you're looking at that entire swath of many, many different emitters, and you want to just do detection on what's out there. Well, if you compare a purely data-driven neural network approach to the kind of traditional radiometer-based approach, there's pretty substantial sensitivity and computational complexity gains as well. So in this case, you're on the order of 8 to 10 dB more sensitive for many types of signals than you would be using just a simple radiometer, because it can do this kind of pattern recognition that we do as well when we look at a spectrogram or a T&M instrument manually. So it's really exciting to see these tools extending not just to classification, but also to detection, so that we can really have these comprehensive pictures of what's going on in the spectrum around our devices. So, our focus then putting this all together into a set of mature software that can very quickly understand what's going on around any kind of a wireless, a G Node B or wireless device, is reaching kind of levels of precision recall where we can get to very, very high accuracies on the order of 1 or 2 milliseconds worth of data, which is really exciting because we can now understand and respond to what's going on in the spectrum very rapidly and with information about what's actually out there. So for many different applications across spectrum monitoring, multiple access schemes, multiple G Node B sharing, and across security applications, now really has a wealth of information to leverage in real time by using these sorts of front ends that we've never really had before. So this adds a lot of interesting things you can do. It used to be that if I wanted to record RF data off of a radio device for a second, it might be a terabyte of data. It's just this massive flood of raw sample data off of a analog digital converter. But if we're able to digest it now into this nice structured data about emissions and what's going on in the spectrum, we can now start to build these time series directly of RAN activity over days and months and years within manageable volumes of data. And this is exciting because we can turn the RAN almost into the type of analytics that we can do on our wired networks today, so that we can use kind of mature CMs and monitoring tools to understand what's going on. And then we can use this to recognize changes or anomalies or degradation in the network. So rather than having to rely on network level KPIs to guess at what's going wrong in the network, we have these very clear RAN-based indicators that can recognize these things very quickly. And so this is actually some activity uplink. So this is 4G uplink activity in the university over a week, where you're seeing basically a normal week, and this is basically uplink burst packet counts on one carrier band for a work week versus a holiday week. And so these sorts of trends are very discernible, and you can now start to do analytics directly on the RAN without access to the network activity. And likewise, once we have these sorts of time sequences, we can really start to apply some of the more state-of-the-art time series prediction modeling approaches to get a better idea of what RAN utilization will look like over time. And then recognize when it deviates from that prediction. So, where is this all going? I think there's a lot of immediate applications in the 5G RAN and even in optimization of existing 4G RAN. But I think if we start to look even forward to beyond 5G, where we're trying to really improve spectral efficiency by an order of magnitude, we're trying to improve data rates by an order of magnitude, we're trying to drive down the computational complexity by an order of magnitude. All of these design goals, then that what we talked about with learning to encode and decode from this channel is just kind of the beginning of the problem. There's all of these aspects around how do we learn and feedback channel state information, how do we shape the frame layout and the pilot layout within these frames, how do we condition all of these aspects based on the dynamics within cells, so around known mobility models like streets passing by or hallways or walkways. How do we really leverage this location and specific geometry of sectors to improve all of these aspects? And then how do we really build in these feedback flows? So, the core of online learning is having some path by which to do this feedback and continued optimization. So how do we build this into our future protocols? And then, we've been looking a lot at, machine learning driven spatial processing. So both for MIMO and for direction finding. And I think as we go beyond the massive MIMO systems we're deploying today, there's a lot of talk about, how do we leverage smart surfaces? How do we leverage, non-uniform distributed arrays to get even more dense, many users, high spectral efficiency deployments? And I think that, these are problems that we can't solve with a lot of the traditional array processing algorithms. And so I think this is another really exciting area where there's tons of potential for much more efficient many antenna, many user spatial processing in these kind of nonlinear processing algorithms. And then really scaling this down. So one of the things we've seen is even in low antenna count, like 4 TRX 5G deployments, we can drive down the computational complexity using some of these smaller neural network approaches. So I think the potential as the computing infrastructure becomes more and more efficient for deploying these neural network solutions, there's a ton of potential to make even smaller and lower power IoT devices as we go forward. So really, just learning and exploiting much more information about cell geometries, user behaviors, and trying to exploit this to make our systems much more efficient is kind of the trend that I see as the core to making the L1 much more efficient over time. So, I mean, I think we're very focused on an incremental approach to this, looking at what we can do today in today's systems, and then starting to look at, where could this go over time as the standards are interested in bringing in some of these features. And that's pretty much it. So, we're excited to be building out some of these prototype systems for kind of bringing ML capabilities into the 5G OpenRAN ecosystem, as well as some of the sensing efforts. So we're growing. We're very excited about this space and the growth of OpenRAN over the past year to help enable this. So we're always looking to work with folks and would love to chat with a number of you, with interest in this area. So, thanks.
Thank you, Tim. Thanks for the nice talk. And we have time now to take questions. And please, you can write on the chat and em português. Basically, pessoal, vocês podem escrever no chat se preferirem que a gente traduza. E aí nós tentaremos então traduzir se quiserem escrever em português. So I believe that we are going to benefit because Tim is not only doing state-of-art academic research, but actually building machine learning-based telecom systems and productifying them, so we can learn a lot. And the first question I wrote to invite people to write more is regarding measurement data. And because you have been involved with GNU Radio, software-defined radio, etc., and now with OpenRAN, maybe you see the let's say decreasing price for equipment like commercial grade equipment. So my question is, do you have advices to researchers in Brazil to collect data without much money, like this first question in the chat?
Yeah, I think so. This IEEE Machine Learning for Communications initiative, one of their big focuses is on data sets and helping to build and promote good data sets. So I know that there are some really nice data sets out there available online that you can go and do some really interesting work with today. So I would definitely encourage you to make sure you look at what's out there because creating data sets is time consuming. and it can be a big effort. But there's also, software radio, I think, has become more and more accessible. So, there's always some hardware and cost in terms of whether it's a USRP or an RTL SDR or a Lime SDR. There's a lot of different radios that you could use, but beyond that, I think, tools like GNU Radio or like SRS, LTE, or things like OpenRAN interface are really, really powerful tools to let you do UE or G-Node B simulation, so that you can take kind of software radio and then free software and be able to produce a lot of those data sets internally. So, I think, open source is a huge enabler to be able to run some of these systems where, maybe before I needed a very expensive piece of test equipment. But now if I have a software radio, I can simulate almost everything with a little bit of software. So I would definitely take advantage of those as well.
Okay. Okay, thanks. We have another question. I guess you can see on the chat window. It's basically about the integration of IoT, non-3GPP, like low power wide area networks to 5G and 6G in future, and also applying artificial intelligence in those scenarios. From Antonio Carlos.
Yeah, it's a good question. I think till today they've been largely separated on different bands. But I think that, if we do see things like the 6 gigahertz band being opened up for shared use between private 3GPP and Wi-Fi and then LPWAN systems, then I think that it's going to be a very interesting interoperability problem. And I don't know that the industry has put enough thought into that, because ultimately we need some way to sense and understand what's going on between all of those systems. So, I think, my initial thought is that having sensing for awareness of what other systems are nearby is critical for these systems to be able to kind of self-organize in a reasonable way. We've certainly seen in the US some of the more database-driven approach, and there may be some more of that as well, like deconflicting interference through more centralized databases. But I think, both on the sensing and awareness side, and on, if you look at learning new L1 modulation schemes that are kind of more robust to certain types of interference, I think there's a lot of interesting opportunities to maybe like learn LPWAN protocols that are much less susceptible to interference from 5G systems or from Wi-Fi systems than they are today. So I think it's going to be interesting to watch this very heterogeneous set of wireless systems emerge and leverage these technologies.
Okay, the other question from Professor Luis Meloni: do DeepSync software need dedicated hardware platforms for real-time use?
So everything that we're building is software that can target a number of different platforms. So your performance will kind of vary based on what you're running it on. I think, we've been heavy users of NVIDIA and kind of off-the-shelf graphics processors to run a lot of these algorithms. And so again, that's kind of nice because you have this large economy of scale to drive down the cost for these hardware systems, to be able to run, very fast signal processing algorithms in real time. But it depends on the application. I think for a lot of these systems, like if we're talking about sensing in multi-protocol and multi-user environments, we may not need to do it very rapidly. You may not need to run it on every sample. So I think there's a wide range of what are the applications and how fast do they really need to run some of these inference algorithms.
Okay. I ask it because this question regarding the channel with respect to problems, for example, when you are trying to back propagate the error and you have to take the channel in account, or you have to actually do some sorts of simulation to get the data. And so my question is, could you elaborate more and share your view about how to take the channeling accounts when training these end-to-end physical layer systems?
Yeah, definitely. So I think right now there's kind of, I'd say, three classes of approaches to trying to train these end-to-end autoencoder-based systems over a real channel. And they all kind of have their own pros and cons. So there's methods that try to emulate the channel. So we've done things with like generative models to try to measure and then simulate the channel response so that we can then differentiate through it when we're optimizing the autoencoder. Then there's these kind of iterative methods that are using more of a reinforcement learning or a policy gradient approach to try to iteratively tune the encoder and then the decoder. And they're using this kind of variational method on the transmit side to explore that surface, which gives you a way to approximate gradients over the channel because you don't actually have a closed form expression for the channel. And then there's been some other really interesting kind of variational methods that have looked at just trying to approximate gradients over the channel using a few different approaches. And I think all of these are very powerful, but there's a lot of factors. So you have to really consider, how fast is the channel, how fast are the channel statistics changing? How much data do you have then to try to learn the statistics of the channel? And so I think, we're to the point where these methods work really, really well in stable channels. But, certainly one of the major challenges for the field is, as the statistics of the channel change wildly and very quickly, how do we effectively do learning? And you can learn against much more aggregate distributions in those cases, but you don't have as much data to do learning on. And so I think ultimately it comes all the way, in the very worst case, you wind up coming back to the point that your channel is changing so wildly that the only good model you have for the channel is this kind of simple statistical model that we've started with. And you kind of wind up back to where I can't leverage data to improve the system because it's just not stable enough.
I see, I understand. And how about the number of antennas? Is it an issue, like a MIMO system, for example, being much more complicated, or not?
We've seen these methods to work very well still in multi-antenna systems. But again, I mean, there's a lot of information theory on the learning side, which has yet to be formalized. So for instance, if we're trying to learn an 8x1 system that's basically a diversity receiver, the learning information capacity is very high. And so it will converge very quickly to a nice, very, very good solution. But if you're trying to learn like an 8x8 system where you have 8 different information streams and you only have 8 observation points, so it's not over-determined at all, then you don't have a lot of learning capacity, and so it makes this learning process much harder. And so in those cases, we often have to do things like start with the network in a good solution or in what the traditional solution would be, and then allow it to adapt from there. rather than trying to just start from scratch and converge to a good solution.
I see. I see. I see. Any other question from the chat? I don't see any. So maybe then we can close it here. Thanks, Tim, for the nice talk. And we hope to see you again, but next time, of course, here in Brazil, such that we can show you beautiful places and chats personally. So we are very grateful that you accepted our invitation again, and hope you have a successful 6G and other implementations using machine learning in future. Thanks a lot.
Well, thank you guys. I appreciate the chance to talk, and I hope I'll be able to make it there in person someday soon.
Ok. Thank you. Bye bye. Obrigado, pessoal. Tchau, tchau.